So last time we talked about chapter 6, which was a short little chapter about balancing equations. So remember that whenever you have an equation, you always want to make sure that it's balanced. And to balance it, we do change just the coefficients, none of the subscripts along the way. So in this chapter, we're going to talk about different types of reactions and different ways to classify reactions. And as we will see, there are definitely multiple ways you could classify, for example, the same reaction, depending on sort of what you're looking at. So the first thing we're going to talk about is sort of aqueous solutions. And a aqueous substance has that AQ symbol next to it that we talked about a little bit, I think, previously as well. And AQ basically means a solution which is a homogeneous mixture. It is different than something that has the L sort of connotation there to it. Although they are both in the liquid phase, something with an L is usually a pure substance like water. So that's usually just a pure substance. And aqueous is a mixture, which means you do have two things that have been mixed together. So again, if you took something like water and you added some sodium chloride solid to it, that salt will dissolve and it will make a sodium chloride solution, which will get the aqueous sort of symbol next to it. So aqueous is a solution. A solution really is a mixture of two or more substances together. And usually when we talk about a solution, there is two parts to the solution. There's the solute, which is the smaller part of the solution, and there's the solvent, which is the larger part of the solution. Now, in my example up here, again, the water would be the larger part of the solution, so that would be our solvent. And the sodium chloride here would be the smaller part, and that would be the solute. The good news again is if you do have a solution such as this, whatever the, thank you very much, whatever the name of the solution is, like in this case sodium chloride, that's always going to be the solute. So if you have a sodium chloride solution, the solute is going to be sodium chloride. If you have a potassium chloride, it'll be potassium chloride. If it's an ionic sort of solution, probably 99 times out of 100, even more, the solvent most likely will be water. So water works really well with ionic sort of substances, and usually that is the solvent as well. Water is not always a good solvent. So for example, if you're making like a chlorine water solution, water would not be a great solvent for that. Now, an electrolyte, which we talked about in a previous sort of chapter, are things that will dissolve in water and create electricity. Remember, electrolyte is something that will basically break apart into ions. And it's those presence of those ions which allow it to conduct electricity. And there's a few different types of electrolytes. There are strong electrolytes, weak electrolytes, and there's also things that are non-electrolytes. And non-electrolytes do not conduct electricity because when they do dissolve in water, they do not form ions. So non-electrolytes do not form ions. And again, it's the presence of the ions which really help conduct electricity. And in the case of a non-electrolyte, they are not formed, so they do not conduct electricity. Now, strong electrolytes, as a reminder, are things that basically 100% break apart into ions. So again here, if you have something that's a strong electrolyte, and most ionic compounds that are solutions are strong electrolytes. So if you had, for example, a beaker of sodium chloride solution, inside that sort of beaker, you would have 100% sodium ions and 100% chloride ions. So you would have 100% of the ions present. You would have none of the sodium chloride sort of ions or units together. So if you were to look at that sort of beaker, you basically would just have nothing but ions floating around. And because of that, it's a very strong electrolyte because you have lots and lots of ions basically floating around in that solution. Now, when we do that, it does conduct a lot of electricity and it completely breaks apart. And remember as well, we do have some non-electrolytes, not non-electrolytes, we have some weak electrolytes. And weak electrolytes mainly stay together. But do break apart a little bit. So something like hydrofluoric acid is a weak electrolyte. It will break apart into H plus and F minus in solution. And we do have these arrows that are heading in both directions, which means, again, this is a reversible reaction. And it does go in the forward and reverse direction. So different, again, is if you take a look at a weak electrolyte, you will mainly have the HF ions, the HF compound together, and it will produce a little bit of ions floating around. And unlike our strong electrolyte that we just saw there, like sodium chloride, where you have none of the whole units still together, again, that is the major difference there here with our strong electrolyte here as well. Now, again, some strong electrolytes are strong acids, like HCl, HNO3, perchloric acid, sulfuric acid, hydrobromic acid, and hydroiodic acid. Those are some strong acids or strong electrolytes. Also, some strong bases are also strong electrolytes. So strong bases like sodium hydroxide, potassium hydroxide, etc. Also, a lot of ionic compounds are strong electrolytes. They will break apart. So a lot of weak electrolytes are weak acids and weak bases. So HF is a weak acid, acetic acid also another weak acid, nitrous acid, etc. So again, as we might have talked about previously, sort of knowing these strong acids are sometimes good when you're thinking about electrolytes, because if it is one of these strong acids, then you know it's a strong electrolyte. If you could recognize it as an acid but not one of those six, then you could probably make a pretty safe bet that's going to be a weak electrolyte and sort of stay together. I would say in terms of weak bases, ammonia is probably your most common weak base. A lot of organic compounds that contain nitrogen are weak bases, as well. Now, water, when we do have something that will dissolve in water, water is a really effective solvent for a lot of ionic compounds, and that is because water is polar. So again, there is a positive side to water and a negative side to water. And when we look at water, like we talked about in bonding, the oxygen side is more negative, and the hydrogen side, because of its dipole moment, is more positive. And that works really well when something that's ionic wants to dissolve in water. What happens is water is able to basically surround those ions in solution. And for example, the positive cation here can get surrounded by the negative side of water, which would be the oxygen side. And the anion here can also be surrounded, which is the negative ion, by the positive side of water, which in this case would be the hydrogen. So water works really well. And remember that when you do dissolve something that's an ionic compound in water, it is a physical change that's occurring, right? It's not a chemical change that's occurring. Although the solid disappears, it just disappears because basically they're surrounded by a ton of water molecules and it's no longer visible to your naked eye to see the solid still in the solution. It basically gets surrounded. You help this process out a lot by obviously stirring it and mixing it, and that allows all the water molecules basically to surround those ions. It also allows them to break apart. And this process here is what is sometimes referred to as hydration. And again, is a physical change because, frankly, the water does two things. It allows basically the sodium chloride or ionic compound to dissolve where it's no longer visible to our eye. Uh, but it also prevents really the two ions from coming back together because that is a really, really strong attractive force. It's only able to kind of keep them apart because there's just so many water molecules, for example, in your beaker or whatever it may be. But we know what will happen if we heat this up, right? So if we started to heat this up, we will now start to see really our water molecules start to evaporate. And when the water molecules evaporate off, there is nothing in the way of those two ions from coming back together, and you will once again see that solid reform. We did, I think, a couple of these earlier on in the semester where you took your evaporating dish and put your solution up there, evaporated off all the water, and you're left with that kind of solid residue that's left in your evaporating dish. And again, once you've evaporated off all the water, there's really nothing to prevent that really strong attraction between the solid, the positive ion and the negative ion from coming back to make that solid. And that's a really, really strong attraction. Questions on that there? All right. So as I mentioned a second ago, we have some strong electrolytes and some weak electrolytes. And again, a lot of strong acids, ionic compounds are strong electrolytes. Uh, our weak electrolytes are our weak acids and really our weak bases. So this is acetic acid here, which is the major acid in vinegar. It's obviously not negative or anything. And again, when it breaks apart, what you really have in solution is this guy will actually stay together, but it will produce a few of these ions here. And again, that is different than as we talked about where we have going on here, where it's going to 100% break apart. And again, you have none of these guys still together in the solution, just completely ion, basically filling that solution. So now we understand again electrolytes. We're going to talk about types of reactions. And when we talk about types of reactions, there's really two big categories of reactions that you can basically break apart into. And there's also three reasons why a reaction takes place. And really, those three reasons why a reaction takes place is you formed a solid, which is sometimes referred to as a precipitate. You formed water, or you had an electron being transferred. So pretty much all chemical reactions breaks down to basically one of those three things happening. Either, again, you make a solid, you make water, or some type of electron transferred. So these are the two big classifications of reactions. And as we will see underneath each of these classifications, you can identify a reaction even more specifically through another name. So in a double displacement reaction, as we will talk about, they always occur the same way. And the way you can recognize a double displacement reaction is it is the only type of reaction where you will be starting out with two ionic compounds. So two ionic compounds are reacting, and that is basically how you can recognize that it is a double displacement reaction. And once you recognize that it is a double displacement reaction, as soon as you do, it always works the same way, which is the two positive guys will basically switch partners. So the two positive guys will basically go and just switch partners. And the result of that is you will actually form two new ionic compounds on the other side. You'll make a new one here, and these two guys will come together to make a new one on that side. So you kind of start with two ionic compounds and you end with two ionic compounds. It's basically the trademark of a double displacement. Now, double displacement reactions basically account for the first and second reason why a reaction takes place, and that is either the solid being formed or water being formed. So, as a result of these ion switching partners, in some cases, one of these guys will make a solid. And again, that accounts for what is basically one of the three reasons why it takes place. In other cases, you may not make a solid, but one of these guys may make water as a result of it. And double displacement, as I mentioned, is basically accounts for two of the three reasons why a reaction takes place. And ultimately, those two things is what's happening, either precipitate or water is being made. Now, redox reactions involve basically the third reason why a reaction takes place, which is an electron transfer. So, if it is not a double displacement reaction in terms of the big category, pretty much all other reactions will fall under the big umbrella of redox reactions. So, you could think of double displacement reactions and redox reactions as these big sort of umbrellas of classifications. And underneath those kind of big classifications, as we will see, you can more specifically classify a reaction another way. But ultimately, this still like a double displacement reaction or a redox reaction that's happening is one of those two types of reactions. All right, so let's take a look first off at precipitation reactions. And precipitation reactions do fall under the big umbrella of double displacement reactions. So a precipitation reaction is a more specific classification of a double displacement reaction. So in this one, for sure, when you do that double displacement and you switch partners, you will form a solid on the other side along the way. All right, so let's take a look here. So in a precipitation reaction, a precipitate is formed, and sometimes a precipitate is abbreviated PPT. So if you see PPT, it stands for a precipitate has been made. So what happens when you basically do a precipitation reaction or a double displacement reaction is, you got A and B plus C and D, for example. And basically, what you have in the solution are these ions floating around. So they're basically strong electrolytes in most cases, and they will be just a bunch of ions basically floating around in the solution. And what happens in a precipitation reaction is when they do switch partners, one we'll just use here, for example, A and D. When A and D are floating around, they're going to be attracted to each other and they will actually make a solid and they will come out of solution, make this thing a little cloudier, make an actual solid that maybe drops out of solution. And those guys will make a solid. It will typically leave the other ions just still floating around in the solution, and they're not really attracted to each other, and they're not coming together. But it's these two that come together to make this solid and comes out of solution. And again, that is a precipitate that would be formed. In real life, again, a precipitate does not have to be like a rock hard solid, like it comes together and just drops out like a rock or something like that. It can be that it comes together and maybe the solution now looks a lot cloudier than it did before. There's some particles floating around in the solution that wasn't previously there. So again, when a precipitate is formed, it doesn't mean it has to be sort of a rock hard solid just going to like drop to the bottom. Again, it can just be cloudiness and stuff like that. And that cloudiness is the solid or precipitate has been formed. So if we take a look at this reaction, which is essentially the reaction we're going to do next week, I think. We take lead 2 iodide plus some sodium iodide, lead 2 nitrate and sodium iodide. And we know this is a double displacement because this is an ionic compound and this is an ionic compound. And again, as soon as I know that, I know this is a double displacement reaction that's taking place. And we're going to basically switch partners here. So the lead will come over here and this guy will come over here. So when they do come together, they do make some new ionic compounds on their side. So this guy and this guy comes together. And when those two ions come together, that is going to make a solid that is formed. And when sodium comes together and the nitrate comes together, they will make sodium nitrate. Now, one of the important things when you look at an equation like this, and this is what is known as the molecular equation, which is obviously everything written as normal sort of formulas and stuff like that. Now, one of the important things, though, that people oftentimes screw up on when they have this, and especially when they have this part of it, and this goes back to something we maybe talked about in the previous chapter, which is, let's just say in this case, we had just the starting stuff here, just the reactants, and we wanted to predict the product. So remember that if you were asked to sort of predict the products, which you might have to do, the thing that you want to always think about is you want to get the right formulas first and then balance the equation. So what that means in this case is if I take a look at this guy here, the two basic ions that make this up is lead with a +2 charge, and this is just nitrate with a -1 charge. And the two basic ions that make this guy up is a sodium ion and an iodide ion, which is from group 7. So it's really important when you go, if you are not given the product side here, that you get the right formulas first. So we are going to switch partners. So we know that the lead here will end up with the I minus. And what that means is just like you do with nomenclature, we want to equal 0. So that would give us our proper formula here of PbI2, as we would need in this case 2 I minuses to balance out the +2 charge. And the same thing happens when we take our sodium, which is our other one here, which is a +1 charge, will come together with our nitrate that is a -1 charge. And that will give us our proper formula here of NaNO2, NO3. I can't tell you how many people, if they were given this, will write something like Na2NO32 because they're trying to balance and write the formula at the same time. So remember, you don't want to do that. You want to get the formula correct, just like you were doing nomenclature and naming. And once you have the formula, then you could go back and balance out the equation by using, obviously, the coefficients. And obviously, you probably wouldn't have had the 2 there to begin with, but you put the 2 on both sides, and now you'll be balanced. So just keep that in mind as you come across reactions like this, and you will have to predict what's on the product side a number of times. You want to always make sure you get that right formula and then balance it so that you get the proper formulas along the way there. Any questions on that there? So this is the molecular equation, and a reminder that because these are strong electrolytes, we can actually write a formula of what is happening in this case, and this guy is aqueous here. And really, in a solution, when you put these guys together, if you dump both of these guys into a beaker, So if you took this and dumped both of these guys into the beaker, it is basically going to break apart into ions, basically. So we're going to get some lead ions, some nitrate ions, we're going to get some sodium ions, we're going to get some iodide ions kind of coming around along the way. And what's going to happen is we could write another equation to sort of represent what's actually happening in this reaction. And that is we would break apart our lead to nitrate into ions. And so we would have a lead ion. There are two nitrates, so that two comes to the front. And we will end up with that. We would also break apart this guy as it is a strong electrolyte as well, an aqueous. So we would end up with two sodium ions in that solution and two iodide ions. So we'd have like another sodium floating around in there. On the other side, we have this guy, which is a solid. And for it to be a solid, it will stay together. It will not break apart. So typically, if we're writing this type of reaction, anything that is a solid, anything that is a pure liquid, in a lot of cases, gases occasionally you might come across, but also weak electrolytes. So weak electrolytes, anything that's a solid liquid, will stay together and you don't break them apart. So you just keep their formula together. So this is a solid, stays together. And this sodium nitrate will break apart into two sodium ions and two nitrate ions. And this equation here is what is known as the total ionic equation. It is also sometimes called the complete ionic equation, or sometimes people, again, just refer to it as the ionic equation as well. It is an equation that kind of shows exactly it shows sort of what's happening in the actual beaker. So you break apart anything that's a strong electrolyte into ions. Now, when you look at this equation, you should be able to look on both sides of the arrow, and you should be able to find ions that look exactly the same on both sides. So if I look over here, I have two nitrates. If I look over here on the right-hand side, I also have two nitrates. If I look on the left-hand side, I have two sodium ions, and on the right-hand side, I have two sodium ions. These ions, which are exactly the same, and as you also look at there, if you balance the equation properly, will also have the same number of ions on each side. So there's two sodiums on the left, there's also two on the right, there's two nitrates on the left and two on the right. These guys are what are referred to as being spectator ions. So these are spectator ions. And if you are a spectator, you are basically just watching what's going on. And that's what's happening with these ions. They are in the solution, they're floating around, but they're really not making any of the products. They're really not the thing that's producing the product in this case. They're just kind of there really to balance out the charge. So what we do with spectator ions is on the left-hand side and right-hand side, we just cross them out. And what we're left with is a third type of equation. And in this case, this is the lead 2 ions and the two iodide ions. Form our solid here, our lead 2 iodide. This is what is known as the net ionic equation. And the net ionic equation is the one that basically tells you what is happening in this reaction. So basically what happens in this reaction is when you put the lead 2 nitrate in and when you put the sodium iodide into the solution, it is the lead 2 ions that goes and finds the iodide ions, and they form this solid basically in this case. And that is ultimately what is happening in this reaction. As you can see there in the picture, our sodium ions, our nitrate ions, they're just floating around. They are not coming together. They're just having a good swim basically. but it's the lead and the two iodines that are going to come together and make this solid and basically take everybody out of the pool, if you will, as a solid in this case. So these are three important types of reactions or equations that we write. One is the molecular equation, which we just write with normal formulas, and we balance it like obviously like normal. We then can break apart that molecular equation into the total ionic equation. And the total ionic equation, like I said before, will break apart anything that is technically a strong electrolyte into ions. Anything, again, that's a weak electrolyte, a solid or a liquid, will stay together. And from your total ionic equation, you can find ions on both sides of the arrow that look exactly the same, and again, should have the exact same number of ions present, and that would be your spectator ions. Those guys you cancel out, and what you're left with is the net ionic equation, which is ultimately the reaction that's happening in this case, which again is our lead and our iodide coming together in this example. If you get to the total ionic equation and you get to your spectator ions and you do not have the same number of ions on each side, you balance the equation incorrectly. So the spectator ions should always completely cancel out and should always have the same number on each side. And again, it's a way you could check yourself if you get to that step and you definitely don't have the same number of ions on each side, they are going to cancel out. Any questions on that there? Okay. Now, obviously here, this reaction is a double displacement reaction. This reaction is more specifically called a precipitation reaction because it makes a precipitate or a solid is formed here. So again, a precipitation reaction accounts for one of the three reasons why a reaction takes place. It is also, again, a more specific classification of a double displacement reaction. So same thing happening here. Yeah. It's aqueous. Yeah, yeah. That's, all those little guys are aqueous except for the PBI2 is a solid. Yep. So AQ. Other questions? All right. So again, here's basically what we just went through there. Got our spectator ions, which again can be found on each side of the arrow. And what we're left with is our net ionic equation. Now, in order to predict whether or not when we do a reaction like this, if we put these ions together, will we get a solid or not? We do have to know something about solubility. And solubility helps us predict whether or not we would expect a solid to form if we kind of combo these two ions together. Um, and solubility, if something is soluble, that basically means that it will dissolve and you would not expect a solid to form. If something is insoluble, you would expect a solid to form. So when we use solubility rules, which we're going to look at here in just a second, if something is soluble, it will get that aqueous symbol next to it. So, and it means you would not expect a solid to form. If something is insoluble, it would get the solid symbol next to it. And again, that would mean that we would have a precipitate like we just saw there with the PBI2. That is insoluble, which means we would expect a solid. There is a third classification that you sometimes do come across, and that is what is known as slightly soluble. And for all intents purposes, most people consider slightly soluble to be insoluble, kind of leaning towards the insoluble side. So let's take a look at some of these solubility rules. So these are solubility rules, and these are things that are typically soluble under normal conditions in water. So these are guys that normally would have an AQ next to it, which means you would not expect a solid to form. So if you look at a formula for an ionic compound and you see anybody from group 1, you're good to go to write aqueous next to it. It's not going to make a solid. So if you see something like with a sodium, a potassium, anybody there in the formula from group one, you don't really have to look any further. There's no exceptions, which means you should not expect a solid to form. You can put aqueous next to it. Anything with ammonium in it also going to be soluble. There's also no exceptions to it, which means as soon as you see NH4 in your formula, you know that that is not going to be a solid. That's going to be something that's going to be a solution. It's going to be aqueous. Anything that contains nitrate, chlorate, or perchlorate. So again, if you see a formula that has NO3 in it, you automatically know it's going to be soluble in aqueous. You would not expect any type of solid to form. Anything that has chloride, bromide, or iodide in it, you would expect it to be soluble and again get the aqueous symbol. But when we get to these three, there are some exceptions. And there are three exceptions that go with this, which means that if you have chloride, bromide, or iodide, and they are not with silver, that's mercury 1, or lead 2, they will be soluble. But if you have chloride, iodide, or bromide, and they're hooked up with lead, silver, or mercury, they are actually going to be an exception and do the opposite, and you would expect a solid to form. And our example there, right, was on the last one we just did, PbI2. This is lead and iodide. So normally iodine is soluble, but because in this particular case it hooked up with lead, it's going to be the opposite and an exception, and it will actually be a solid that forms. So that is why when we put lead and iodine together, we get this yellow solid. Now, most sulfates are soluble, which means we would expect it to be aqueous. There is some exceptions. So there are some exceptions that are calcium and silver sulfate are slightly soluble, and barium, mercury 2, and lead sulfate are insoluble. So again, if you have any of those guys there as the exception, the opposite sort of happens, and we would expect them to end up with a solid versus aqueous. So there are some solubility rules that have no exceptions, and it's like if I see it, I'm good to go. They're going to be aqueous. But there are some that are normally going to be aqueous and soluble. But if you have one of the exceptions, it does the opposite and becomes insoluble. Again, and slightly soluble, most people consider to be insoluble. Any questions on that there? Now, here are some rules of things that are typically insoluble. So these are guys that typically, if they are present, will typically give us the solid or a precipitate to form. Hydroxides are typically insoluble, but there are some exceptions, and the exceptions are pretty much the same thing we saw on the previous slide, which is anything in group 1 and barium and calcium hydroxide are slightly soluble. So again, in this case, this guy here would then become soluble. The opposite. I'm sorry. It's not soluble. It becomes soluble, AQ, not solid. Carbonates, phosphates, and sulfides are typically insoluble, so they typically will make solids, except if you have group 1. So the good news is you can just remember the group 1, and that takes care of your exceptions on here. You'll be fine. So they will become soluble, the opposite here. Which would be aqueous. So these are solubility rules that help us decide what's going to make a solid or not. Here's another kind of version of that from your book. And again, basically everything on this side should be aqueous and no solid form. If you have any of these exceptions, they will be a solid. Everything over here are typically solids, but if you have any of these exceptions down here, they will become aqueous. So again, these are sort of your solubility rules that you do need to know, and they expect you to know it here. So again, this is a table from your book, which might be an easier way maybe to kind of look at it. Any questions on that there? Okay, so let's just say we had something like we wanted to combine. Let's do silver nitrate, and we'll do some sodium bromide. So why don't you write the rest of the equation and also balance it? Maybe we'll do it here on this side of the room here. So silver nitrate and sodium bromide, and let's do ammonium sulfide and iron 3 chloride here. All right, so for each of these, uh, write the molecular equation. Why don't you write the total ionic equation? Why don't you also write the net ionic equation? Why don't you also find the spectator ions, yeah, for both of them. Use the solubility rules as well to figure out aqueous. And when you have something like this, what you want to think about is what type of reaction is happening, and hopefully you can recognize this is a positive negative guy, a positive negative guy. So again, we have two ionic compounds, which means that is pretty much going to be, go that way. That's going to be a double displacement reaction. So once you do that, you should automatically know we're just going to kind of switch partners. So remember, as we talked about, we want to make sure that we get the correct formulas down first. So we're going to take a silver that has a +1 charge and put it together with a Br that has a -1 charge. So that's basically silver and nitrate. And this is sodium and bromide. So we're going to take this guy and this guy together. That's going to give us our proper formula here of AgBr. We are going to take the sodium that's +1 and the nitrate that's -1 and put it together here, just like we were doing nomenclature, and that will give us our sodium nitrate in this case. Now that we have the proper formulas down, we want to then go back now and balance it. And in this particular case, we actually are balanced, as we have basically one silver on each side, one nitrate on each side, one bromine on each side, and one sodium. So it actually is balanced. First off, any questions on that there? Now that we have all of our formulas, we could use our solubility rules here to determine, are they going to be aqueous? Are they going to be a solid? So when I look at the first one here, although I may not be able to see silver, I definitely see nitrate. And when I look at the solubility rules, I could find nitrate right here, and there are no exceptions, and that is in the soluble category. So I automatically know as soon as I see that nitrate that I can put the AQ or aqueous symbol next to it. Now, when I roll over to the next one, as soon as I see sodium, I know that this is group 1 on the periodic table, which falls right here on this side, and there are no exceptions. And I automatically know that this is going to be aqueous as well. So I do not need to actually look at the bromine, but I could look at the bromine. And if I look at the bromine, it also is soluble, but there are three exceptions, which is silver, lead, and mercury. And in this case, my sodium is, or my bromine is with sodium, which is not one of the exceptions. So it would also tell me that it is aqueous. Coming here, if I look at my bromine, It is soluble in everything except silver, mercury, and lead. And in this particular case, it is actually hooked up with silver, which means it's going to be the opposite and going to be a solid. So this will be our precipitate in this case. This would be our solid that's going to be formed here, which is our silver bromide. If we look at the last one, that is sodium, and that's really as far as I need to look. I know that that's going to be aqueous based on the rules. I could also look at nitrate, which is also aqueous, and there's no exceptions for either one of them. So you could actually look at them. So when you're using your solubility rules, you can at least find one of the things in the ionic compound to help you decide is it aqueous or solid. In some cases, like the last one there, you could actually find both of them, and they both should tell you the same thing, that they're either aqueous or solid, depending on what you look at. First off, any questions on that there? That would be our molecular equation, right? Our balanced molecular equation. We can now write our total ionic equation. So this is a strong electrolyte, which means in solution, it will not stay together. It will break apart into a silver ion and a nitrate ion. And because this is an ionic equation, we do need to make sure that we include the charges on our ions. So they are not ions if they don't have charges. So you need the pluses and the minuses here to be correct. Same thing here. This is a strong electrolyte, which means it will break apart into a sodium ion and a bromide ion. When we come to the other side, this is a solid, and the only way for it to be a solid is it has to stay together. Otherwise, it would just be ions floating around in the solution. So we do not break this guy apart, and we do keep it together. This will break apart as it's a strong electrolyte into a sodium ion and a nitrate ion. And this would be our total ionic equation. And again, the important parts here are the states and also the charges. On things that are ions, they do need to have the charges. Any questions on that equation there? Once again, we could use this equation to help us find our spectator ions, and they should be the ions that look exactly the same on both sides. So once again, here we see nitrate, and we see nitrate, and we see sodium and sodium, which are exactly the same on both sides. They have the exact same charge, they look exactly the same, and there's the exact same amount of them on each side. And these guys here again will be our spectator ions. Once again, we just cross out our spectator ions. And what we are left with is our third type of equation, which is the silver and the bromide will come together. And it will make this precipitate that is silver bromide, and this is our net ionic equation, which again is ultimately telling us what is truly happening in this reaction. Any questions on any of those equations there? Okay, let's take a look at the second one here. This is a positive guy, negative guy, positive guy, negative guy. So once again, we have two ionic compounds. And as we've been talking about, only situation this occurs is double displacement. So we're going to switch partners. Once again, we want to look at this and think about the two basic units that make up each of these. This is an ammonium ion, and this is a sulfide ion. And this is an iron with a +3, and this is a chloride with a -1. So once again, when we switch partners, it is going to be the ammonium and the chloride coming together. And it's going to be the iron and the sulfide coming together. So ammonium is +1 and chloride is -1, which means on this side we end up with NH4Cl. Again, no weird thing like NH4 2Cl3 or anything like that. You want to make sure you get the right formula. When we put the iron 3 and the sulfide together, we end up with Fe2S3. 3. Again, proper putting it together. Common number there is 6, so we need 2 irons to get to 6, and 3 sulfurs basically here to get to 6 to balance it out. First off, any questions? Obviously, at this point, I am not balanced, so I do need to balance it. And in this particular case, let's see here, maybe like a 3 here, and maybe a 6 there, and maybe a 2 there. Yeah, that will give me my proper balancing, I hope. That gives me 6 NH4s on each side, gives me 3 S's on each side, 2 irons on each side, and 6 chlorides on each side. So that would represent our balance equation. First off, any questions on that there? All right, now that we have it balanced, now that we have the proper formulas down, we can now use our solubility rules here. And I'm just going to kind of clean it up a little bit here. We use our solubility rules to help us figure out what's solid, what's maybe not solid. So looking at the first one, I see NH4, and looking at my solubility rules, NH4 is right there. It is soluble. There are no exceptions, which means it is going to be aqueous in this case. So I do know as soon as I see that ammonium, I am going to have something that's aqueous. I see here chloride, which I could find on my solubility table here. Chloride is soluble in everything except for silver, mercury, or lead. In this case, my chloride is with iron, which means it is not an exception. So it should be aqueous in this case, and that would give us aqueous. Over here, as soon as I see ammonium, I know it's going to be soluble. And lastly, here I see sulfide, and sulfide are typically insoluble unless it's with group 1, which it is not because it's with iron, and it's not with ammonium because it's with iron. So it is going to be our solid in this case. So this is going to be our solid, our precipitate that is formed in this particular reaction. Any questions on that one there? That again would be our balanced molecular equation in this case. Now, once we do have the balanced molecular equation, we can now write our total ionic equation. Again, we're going to break apart anything that is not a solid. We're not going to break apart a solid, anything that is not a liquid, gas, or weak electrolyte. So here, this first guy would break apart. Now we do have a 3 in front of it, which means we do need to distribute that 3. And since there's also a 2 here, that means there's 2 NH4s, and there's 3 total. So 3 times 2 is 6 NH4 pluses. Yeah, so that is basically where we do with that. The 3 will also get distributed to the S behind it as well. And this is basically 3 times 2. And we will then end up with 3 sulfides with a -2 charge. Any questions on that? Same thing here. We have a 2, which gets distributed to both of those guys. So that's going to then tell us we have 2 iron 3s and 6 chlorides as we distribute it there. Same thing here with this 6 is going to get distributed in terms of the ions behind it. That's going to give us 6 NH4 pluses and 6 chlorides. And our solid here will remain. I'm running out of room, so I'll just go underneath. Fe2S3, and that's going to be a solid in this case. And this would be our total ionic equation in this case. Any questions on that? So people oftentimes have a little trouble when there's some coefficients. You got to distribute. Also, with the subscripts, as you see, it does come to the front. So if you have a coefficient and a subscript, you got to multiply them together. If we don't have a subscript, you would just bring the, coefficient. If you don't have a coefficient, you just bring the subscript to the front. So in this case, we could find our spectator ions. And our spectator ions in this case is, I see 6 NH4s there and there. I see 6 Cls there and 6 Cl's there. So that's going to be our spectator ions in this case. Both of these here. Spectator ions. And again, we're just going to cancel out our spectator ions on both sides. You can think of the arrow like an equal sign. And that's going to leave us 2 Fe3 pluses plus 3 S2 minuses goes to our Fe2S3 solid. And this is our net ionic equation, which is ultimately what's happening here is this precipitate, or solid, is basically what's being formed. And that's why, again, it's called a precipitation reaction. And it's also one of the 3 reasons why a reaction obviously is taking place. Any questions on any of those there? So important again in both the net ionic equation and total ionic equation. Anything that is an ion should have charges associated with it. And again, also sometimes messed up by people. Let's just say we had just one of these here. If we had just one of these, this 2 again goes to the front. And that would give us 2 of the NH4 pluses. In this particular case, we also have that coefficient of 3, which means 3 times 2 gets us to 6 of those. And again, that's how we got to the 6 in that. Any questions on that there? Question on molecular equations, total ionic equations, net ionic equations, how to find spectator ions. Again, obviously, solubility rules are quite important. All right, so we're then going to talk about acid and bases, acid and base reactions. And acid and base reactions also do fall underneath the double displacement reaction. An acid is something that has a sour taste. It can cause litmus paper to change color. So typically if you use litmus paper, which is sometimes used with acid and bases, your litmus paper will turn red and it tells you it's acidic, or if it stays red. It will react with certain metals in a single replacement reaction that we'll talk about later on in this chapter. And obviously strong acids and weak acids can conduct electricity. Bases, on the other hand, have a bitter taste. They feel slippery. A lot of soaps are bases. They will turn litmus paper into blue color, or stay blue, and also they're strong and weak bases, which are strong and weak electrolytes. Acids, for the most part, have the ability to produce H plus, and bases have the ability to produce OH minus. Is sort of your basic sort of definitions of each of those cases. And an acid that can produce H plus, as I mentioned, uh, is really your definition of it. Remember, as we talked about with naming, the cation for all acids is H plus. So the positive guy for all acids is H plus. Remember, your anion is basically your negative guy. So in the case of something like HCl, H plus would be your cation, and Cl minus would be your anion, right? And that is the acid. As I mentioned before, there is a list of some strong acids. And again, those are really good ones to know, because if you know those, by process of elimination, you can determine whether or not this is a strong or a weak acid. Again, the list: HCl, HNO3, H2SO4, HClO4, same one we put up earlier today, HBr, NHI. So those are all going to 100% break apart in a solution. They will not stay together. So if you had any of those in like a total ionic equation, you would break them apart, obviously, into H plus and whatever the negative part is. So something like nitric acid in solution, all you have are the ions. You'll have 0 of the HNO3 units still together. Bases, on the other hand, as I mentioned, are things that can produce hydroxide in solution. And Strong bases are strong electrolytes. So pretty much on the periodic table, if you go lithium, you go sodium, you go potassium, right there to calcium, strontium, or barium. Group 1 and group 2 on the periodic table, if you hook any of these guys up with hydroxide, like sodium hydroxide, potassium hydroxide, calcium hydroxide, these are going to be strong bases. So that's where a lot of our strong bases come from. So something like sodium hydroxide, I don't know why it's an equal sign on your notes, but it should be a plus there. So I'll just write it there. We'll break apart into sodium with a +1 charge and OH minus with a -1 charge. And again, you're going to have 100% the ions in solution, 0% of these guys. So if you have a strong base, basically you will break it apart when you get to the total ionic equation. Now, the reaction of a strong base and a strong acid and a strong base will essentially always make two things. If you take a strong acid and a strong base, you will get basically two things. You will get what is referred to as a salt and water. Water obviously is H2O, and a salt's just an ionic compound that will come together. And this reaction here is also a double displacement reaction. And this double displacement reaction, which is sometimes referred to as an acid-base neutralization reaction, occurs if we took something, say, like hydrochloric acid, which is a strong acid, and we react it with sodium hydroxide, which is a strong base. Again, here, if we look at this positive, positive, and negative, so that is a double displacement reaction that's occurring. And what we know with that is we're just going to switch partners here. And pretty much in this case, when you switch partners, you have H plus and OH minus. And that is where water comes from. So pretty much in this reaction of a strong acid with a strong base, the H from the acid and the OH from the base will come together to make water. And the remaining two things will come together, which is our sodium, which is +1, and our chloride, which is -1. And based on solubility rules, we know that sodium chloride is going to be aqueous. And this is our salt, which is our ionic compound, and this is water. And this is ultimately a double displacement reaction. And it is more specifically called an acid base neutralization reaction, and that is because you basically will form water. And if we went through our three equations, our molecular equation, our total ionic equation, because this is a strong acid, this will break apart into H plus and Cl minus. Because that is a strong base, it will break apart into a sodium ion and a hydroxide ion. Now, water is a liquid, and just like a solid, a liquid, a weak electrolyte will not break apart. So we will keep the water together because it's a liquid. Now, our sodium chloride or our salt is a strong electrolyte, which will break apart to sodium ion and a chloride ion. And this is our total ionic equation. And just like we did previously in our total ionic equation, we could find ions that look exactly the same on both sides of the arrow, and that in this case would be the sodium and the chloride, and these are going to be our spectator ions, just like we had previously. And just like previously with our spectator ions, we will completely cancel it out and leaves us a net ionic equation, there you go, of H plus and OH minus makes H2O. And this is why it is called an acid-base neutralization reaction, because essentially what is happening here is the formation of water. And that is one of the three reasons why a reaction takes place, is that formation of water. And you could take any combination of any strong acid or strong base, and ultimately you will always hit this as your net ionic equation. This is always going to be your final result. And again, that's what accounts for our formation of water. So double displacement reactions through precipitation reactions, which is a more specific classification of a reaction, accounts for solids being formed. Acid-base neutralization reactions, which are also double displacement reactions, basically will form water. And double displacement reactions take care of basically two of the three reasons why a reaction takes place. You make a solid or you make water. Any questions on that there? All right, we'll wrap it up for